Hey guys, so in this video we will be talking about operators acting on superpositions of wave functions. This is going to be our second to last video before we are able to finally arrive at the Schrödinger equation. So the first thing that we'll do is kind of review what a superposition is, even though we did that just a few videos ago, just to get used to actually a new notation. So we know that any wave function, given some observable q, right? Any wave function can be expressed as a superposition, a sum, right? If it's a discrete quantity of the sum over j of phi of c sub j times phi sub q sub j, right? Or we could have psi, so this is discrete, and we can have a continuous quantity q, where psi is the integral from negative infinity to infinity. This is the sum, right? This is the integral over all possible values of q, c sub q, v sub q, dq, right? And this is continuous. Okay, so in fact now I'm going to introduce a new notation, right? And this notation is shorthand. It doesn't really mean anything mathematically. But what I'll write is that psi is this sum integral over q of c sub q phi sub q, right? And what this means is this means that it's a superposition. This is sort of the most general way to write it, right? Because it can be a discrete superposition or a continuous superposition. This symbol over q is just saying this basically means it's either discrete or continuous. It could be either. We don't necessarily have to know. This is sort of just the general way of writing the superposition. So it's a sigma, like a sum, and then an integral in that sigma, and that just means it's the superposition without just acknowledging whether it's discrete or continuous. It's writing it in general. And so now, for any observable q, right, we should be able to write the wave function psi as a superposition of c sub q phi sub q, right? And so if we now act on this with the operator q hat, so I'm going to look at q hat acting on psi, right? Well, this will be q hat acting on this superposition, c sub q phi sub q, right? And now what this is going to do, we have to remember that q hat is linear. And so q hat, one of the properties of a linear operator, is if I've got q hat on a plus b, right, this is q hat on a plus q hat on b. Where if I had q hat on a plus b plus c, this would just be q hat on a plus q hat on b plus q hat on c, right? And if I had like q hat acting on some sum over j of, I don't know, say a sub j, right? This is just summing up a bunch of different things, right? The q hat will go inside, right? Because the sum, or the q hat acting on a sum is the sum of q hat on acting on each part. So this would just be the sum over j of q hat acting on a sub j, right? So this would be, q hat a1 plus q hat a2 plus dot dot dot. And then this is a1 plus a2 plus a3, right? And even more in general, because a sum, or because an integral is just a, a generalization of a sum, we should, a q hat acting on some superposition, some integral, right, of something, I'll just call it, I don't know, a, should be the sum, the superposition of q hat acting on a, right? Because this is true for sums. We just showed that it's true for sums. And for integrals, integrals are just continuous sums, right? So if q hat is linear, this property should be satisfied, that it can go in and out of the sums, right? Because that's what it means to be linear. It acts on each part individually. Hopefully this makes sense, and rewatch it if it doesn't. This is a very important point. So this is now the sum, or the superposition over q of q hat on c sub q phi sub q. C sub q is just going to be a constant, right? Some constant for any given value of q, and so this is that was not great. So the superposition over q of c sub q q hat phi sub q. Well, q hat phi sub q is, so this will be now, finally, the superposition over q of c sub q times q phi sub q, right? Or you could write that as superposition over q of q c sub q phi sub q. Right? And now let's just show an example of this, okay? Because this may seem fairly abstract. Hopefully this will make sense, and I'll show it with this sum. And just trust me, this does work for integrals. It works for superpositions in general. So if I have q hat acting on c1 c1 phi 1 c1 phi 1 plus c2 phi 2 plus c3 phi 3, right? This is q hat acting on this part, right? But the constant can come out. So this would be c1 times q hat phi 1 plus c2 q hat phi 2 plus c3, and you could have these be ket vectors, whatever you want there. I'm just doing this sort of in general to make notation easier. So 3, right? Which is, well, since these are eigenstates, right? So this is c1 q1 phi 1 plus c2 q2 phi 2 plus c3 q3 phi 3, right? Or this is, right, you can just write this as q1 c1 phi 1 plus q2. So it's what this does is it brings that that q, right? It just brings down that q factor, c2 phi 2, right, plus dot dot, right? And so what this is in general, not just for 3, this is just the sum over all possible values of j, q sub j, c sub j, phi, so q sub j, right? And so this could be, I may have been better to write this is phi sub q1, phi sub q2, phi sub q3, but it doesn't really matter. Hopefully you are getting the idea of why this works. And as you know, the superposition, that's one of our superposition postulates, right? So we can do this, and I'm going to do this with a few superpositions. I'm going to do mainly the x hat acting on some psi, right, is going to be the superposition over all values of x, right? Of x, cx, phi x, right? And the momentum operator acting on psi will be some superposition over momentum of the momentum cp phi p, right? That's how the operators work. It's they go inside, and when the operator acts on each part, it brings down it's an eigenvalue, right? And then E hat acting on psi is equal to the uh, superposition over energy of the energy Cp Vp, right? And now usually we'll write this one like as a sum. This one's usually going to be an integral just because of how those variables work. So a lot of times you'll see this written as the sum over n of E sub n. Oh, I don't, this should not have been a p, this should have been an e. Hopefully you caught that. So E sub n, C sub n, phi sub e n, right? So you see this is the same thing. It's just we write it like this, just in general, and then if you you can add the subscripts, right? So if this were a discrete sum, it would be x sub n. If it were an integral, you would have this dx, right? So this is just a shorthand, okay? So hopefully you see it's really just a shorthand of writing in general, a discrete superposition, a continuous superposition when they behave the same, when we're talking about superpositions in general. So hopefully this makes sense, and I will see you in the next video where we use this, right, to get to the Schrodinger equation.